Okay, everybody, this is lecture 18. The title of this lecture is The Big Bang and Dark Matter, and this is the last lecture of the course. So today I want to start off today talking a bit about the theory, the Big Bang theory itself, and then talk about the evidence we have that this actually happened. Okay, so the first piece of evidence that we have that the Big Bang happened starts with the expansion of the universe. So we've been talking about this for a couple of weeks now, that sometime around 1930, evidence began to mount that when you look at galaxies that are all around us, as long as you look at galaxies that aren't super nearby, they're all moving away. And generally this came to be understood as the idea that the universe itself is expanding. Now, it doesn't necessarily mean that we had a Big Bang. If you have a universe that's expanding, this does not obviously imply that the universe began at one point at one time. Okay, so what I want to talk to you today about is some of the evidence that has been accumulated to support this idea of the Big Bang. We've actually talked a little bit about it already in the course, but I haven't really explained to you what the implications are and what the evidence is. Now, the basic idea for the Big Bang theory is that it was hot in the beginning, and now it's cold. And generally this comes about because if you take something that's big, and imagine you have a big container, and you start squeezing it together, you start squeezing it and making it smaller, then the air in that container will get hotter. Okay? And so it's sort of the same deal. If you run the clock backwards, now the universe is big. In the past it was smaller. And one of the big implications of having everything smaller in the past is that it's hotter. So basically that is the Big Bang theory, but the implications of this are pretty interesting. Because as you make things hotter, you change the kind of structures that can exist, and you change the kind of stuff that can actually inhabit the universe. It turns out basically when things are cold, as long as you have energy sources, you can have really complex structures. But if you make things hotter and hotter and hotter, you can't have things that are that complex anymore. Okay, so imagine we're in this room and you start cranking up the heat. If you crank up the heat enough, the seats and everything else in the room will start to melt. Okay, so then let's assume we've all run out of the room. Everything starts to melt. And then you just kind of have this kind of like sloshy soup of stuff in this room. And no longer can you have these kind of complex, hard chairs. Okay, and you certainly couldn't have the complex life that is us. Okay, we would also melt. If you keep cranking up the heat, eventually that liquid would turn into a gas, and then you would just have a really complicated gas. And you can envision continuing to crank up the heat, but basically you can't have anything that interesting if the stuff is getting really hot. And I'll talk a bit more about that in a second. I want to make it clear that I'm not endorsing any TV shows. This is not what I'm talking about. I probably would not endorse that TV show anyway. So the basic idea with the Big Bang theory is that at very early times it's hot. The universe has been expanding and cooling since that time, and today it's quite cold. So, for example, we now think that at about 1 second after the Big Bang, the universe was about 10 to the 10 degrees Kelvin. That's extremely hot. That's crazy hot. In fact, it's so hot at that temperature that all atoms are ionized. So what that means is if you had some hydrogen, the hydrogen, which is basically a proton and electron going around it, it's so hot that the hydrogen actually can't hold on to its electron. And so what you have is something called a plasma, where you basically have nucleons that are going around by themselves and electrons that are going around by themselves. So you can't have atoms in the way that we think of atoms, neutral atoms, when it's that hot. Okay. And in fact, even at that time, it was so hot that even complex nuclei were sort of difficult to make them. But then about 300,000 years after the Big Bang, it got cooler. So as the universe is aging, it's cooling down. As it's expanding, things are getting cooler. And about 300,000 years after the Big Bang, the temperature of the universe was about 3,000 degrees. And it turns out that at that temperature, it was now cool enough that the majority of the atoms could now hold on to their electrons. And the universe suddenly became neutral. And so then you had atoms more like the kind of atoms that we think about as atoms. Now, it turns out that this is a really important time. When the universe went from being ionized to being not ionized, that's a really important time, and we can test for it. But I'll come back to that in a bit. It's now been about 14 billion years since the Big Bang. The most precise number that we have right now is 13.77 billion. So 13.77 billion years since the Big Bang. And the universe is very cold at approximately a temperature of approximately 3 degrees Kelvin. So just 3 degrees above absolute zero, that's the temperature of empty space. Now, this is kind of a diagram of that with the sort of cartoon kind of picture. And so now I've put the Big Bang over here. So this is the beginning, and this is time running this way. And notice that it's not linear time, okay? So now I've got 10 to the minus 35 seconds here, 10 to the minus 20 seconds here, 3 minutes, and 300,000 years. So I'm jumping forward in big chunks of time. That's a logarithmic scale. And that's sort of the kind of scale that makes sense for talking about the kind of things I'm talking about now. Different phases of the history of the universe. Okay. So if you go back to something like about 3 minutes after the Big Bang, that's about the time that light nuclei themselves were being formed. And so around this time onward, what the universe basically consisted of was hydrogen and helium. And that's it. Pretty much the only thing that was made in the Big Bang was hydrogen and helium. And all of the complex chemistry that we have going on today on Earth, the only reason why we have all that complex chemistry is that galaxies and the stars inside those galaxies produced these more complex atoms via fusion, basically. By fusing lighter elements into heavier elements, that's how you built up all of the complex atoms that we have today. Okay, so that includes carbon, nitrogen, oxygen, which are fundamental elements for life. So the universe was born actually with all of these ingredients, as long as you had stoves like stars to cook them up to make them more complex. But it was really only hydrogen and helium that it started with. Now, how do we know all of this? How can I confidently tell you things like this? Because this was a long time ago. So one of the things I've tried to do over and over in this course is try to convince you that we're not just making this stuff up. So we have a lot of reasons to believe the stuff that I'm telling you. So let me talk to you a little bit about the evidence that we have that this thing actually happened this way. So like I said before, just because the universe is expanding, it doesn't mean we had a Big Bang. And what are some of the observational predictions that we have that allow us to test this idea? So the way this works is you say to yourself, well, if this really happened like this, can we figure out any way to go out and observe something that would either refute or confirm this idea? So the only thing you can ever do in science is rule stuff out. Okay? You can't ever prove anything to be absolutely true, but you can rule out things. So one thing we would like to do is say, look, if this really happened, then we should be able to go out and observe X, Y, or Z, and if those things are not observed, then we can rule out the possibility that that happened. Well, the fundamental thing I keep talking about is if the universe was much smaller in the past, it had to be much hotter. And, you know, in around 1930 was the time when people just had first observed that the universe was expanding at all. And right around the 1960s, people began to sort of take this idea seriously, that you run the clock backwards and maybe there was this primordial atom. Maybe there was this Big Bang thing that happened. And theorists like Robert Dicke at Princeton had actually predicted that there should be a glow in the sky left over from this initial hot period. And that the glow that we should observe should be fairly cold today. Something like 3 degrees above absolute zero. And in fact, it should look like a black-body curve. It should look like radiation that if you plot it as a function of wavelength, it should look like that black-body curve, the exact kind of temperature curves that we've been talking about when we talked about stars and other things. Now, the reason for this is actually very interesting. So it goes back to this idea that back before, about 300,000 years after the Big Bang, it was so hot that electrons and atoms, and electrons in the nuclei of atoms were separated. And so what you had is you had nuclei that were zooming around, and you had these free electrons that were zooming around. Okay? Now, if you've got a bunch of electrons that are zooming around, it turns out that light does not propagate very easily through a cloud like that. Electrons like to bounce light around. So basically what this means is it was really foggy. So the early universe before about 300,000 years, it's more like 400,000, but something like 300,000, it was really foggy. And so light could not propagate. So even if you had something that was shining that you wanted to look at, you couldn't see it, because that light coming off of it would bounce off all the free electrons that were around, and you never see anything clearly. So what you had is this kind of, you know, very interesting situation where it was very foggy because it was so hot. But then, so what this means is that before that time, we can't see the light coming to us from that time. We can't look back with telescopes and see stuff that was happening back here. It was too foggy. The light would not get to us. But after this point, after about 300,000 years or so, the atoms grab their electrons suddenly. It becomes cool enough that the atoms can now hang on to those electrons. And suddenly light flies freely. Now, I don't think I actually explained in quite detail why the atoms aren't holding on to their electrons before. Basically what's going on is, imagine you had atoms. It was so hot that they were moving so fast that when they bang into each other, they knock the electrons off. That's basically the idea. But as the universe expands, everything cools down, things start moving more slowly, and that just doesn't happen anymore. So what happens then is, after this point, suddenly the universe becomes transparent. And all the light that was there from this hot universe can start traveling freely. And that's the light that Dicke and others were talking about detecting. So it's that light that they were looking for. Now at this time the universe was about 3,000 degrees. But because the universe is expanding, and what you would imagine then is the universe is 3,000 degrees. And so if you were there at that time and you could look around and measure what the distribution of light coming out looked like, it would look like a black body, and a 3,000 degree black body radiation. But we're looking for light that was emitted then, and the universe is expanding. So the light that's emitted then at fairly short wavelengths associated with 3,000 degrees is stretched out because the universe is expanding. And that stretching out actually stretches the wavelength out into the microwave today. And so what was 3,000 degrees becomes 3 degrees. It's the same, for the same reason that, you know, the universe is just expanding, everything's getting cooler. So what was 3,000 degrees should now be about 3 degrees everywhere you look. Yeah?
Is this light from the Big Bang everywhere in the universe, or like a certain like centralized area? Like,
Right.
Is there a center?
So the question is, where is it coming from? Is it coming from some specific direction that should be like where the Big Bang happened? So the idea is that it happened everywhere, and so this light should be coming from everywhere. No matter where you look, you ought to be able to see this signal, and that's a very important part of this story. So the expectation is that this early universe was 3,000 degrees, and we expect the afterglow of this hot, bright time to be seen today in 3-degree temperatures everywhere we look. Okay? So then about this same time that these theorists in Princeton were making these predictions, there were a couple of physicists at Bell Laboratory named Penzias and Wilson. And they were actually working on a radio telescope, a radio antenna. Now the reason why they were working on a radio antenna had nothing to do with the Big Bang, because it was just a time when radio science was kind of up and coming. So they had built this detector that detected radio waves in the microwave, and they wanted to test it. But they had this problem with it, that everywhere they pointed it in the sky, they kept seeing a signal. No matter where they pointed it, they saw the same signal. It was always about 3 degrees. They didn't know what was going on. So there was bird poop in their antenna. So they climbed in and cleaned out the bird poop. And then they did the observation again, and it's still 3 degrees. And they just have no idea what's going on. And so finally, one of them calls their friend over at Princeton, says, hey, you're a smart guy. Can you think of any reason why when we point our telescope up in the sky, we always get 3 degrees? And at that point, these folks at Princeton knew that they had been scooped. That, in fact, it was these guys who had discovered the afterglow of the Big Bang, which is now called the cosmic microwave background radiation. They found that no matter where they pointed, they see a 3-degree temperature everywhere in the sky. And they were awarded the Nobel Prize in Physics for this. This is one of the really prime pieces of evidence that the Big Bang happened in the way that we thought it would. We thought it did. In fact, there's sort of 4 primary pieces of evidence that people talk about for the Big Bang, at least the 4 I'm going to talk about in this course. The first is the expansion of the universe. We already know about that. The second is this cosmic microwave background radiation, the fact that no matter where you look in the sky, you see 3 degrees. And then there are a couple of other things that I want to talk about very briefly, just to show you that there's just lots and lots of evidence that this happened. The third is something called primordial nucleosynthesis. Primordial means early on, the beginning. Nucleosynthesis means making nuclei. So this is about the kind of nuclei that were made in the very beginning, the kind of atoms that were forged in the Big Bang. And this fourth is the fact that galaxies are seen to evolve. As you look back in time, you see galaxies changing. So we've already covered these first 2, and so now I'm going to go on to this third one. Very briefly, if we want to understand what was going on back here, before this 300,000 year point where the universe got foggy, we can't use light. We can't use telescopes to look back here. So we have to think of other things that we could figure out that we could use to test what was going on here. And so it turns out that the conditions that should have been going on in the universe at about this time were basically the conditions that were appropriate for the formation of light nuclei. So the universe is basically born with primordial particles. Not just atoms, but stuff that's more fundamental than even the atoms. So if you take this analogy of us in this room and you keep heating it up, eventually you have this gas of nothing but atoms. But you could keep heating that room up more. And eventually it starts being so hot, the atoms are moving so fast, they slam into each other and knock the electrons off. And so now you're back to this plasma that I'm talking about, where electrons are free and neutrons are free, or neutrons and protons are sort of going around. It gets so hot that the nuclei can't hang together and you just have free neutrons and protons. But it turns out you can crank it up even more, And even neutrons and protons break apart into their constituent matter, and that's something called quarks. So as you push back towards zero, what's happening is you're breaking all of the stuff up into its most constituent components, the fundamental things that govern it. And so in that sense, it's this region right around the Big Bang itself where you have the real primordial soup. All of the most fundamental constituents of the universe are there in almost elemental form, you know, quotation marks elemental, because it's not those kind of elements on the periodic table. And then from that sort of original initial ingredients, all this other stuff happens and you form. And so the question is, how do you go from the just free neutrons and protons, or the quarks, then to neutrons and protons, and then to atoms themselves, the nuclei of atoms? Okay? And so it turns out about 100 seconds after the Big Bang, when the universe was about 1 billion degrees, this was when conditions were right, densities and temperatures and stuff like that were right, for protons and neutrons to begin actually sticking together to form the actual nuclei of atoms. And it turns out that mostly what's made is hydrogen and helium. And there's also a little bit of lithium that's made. And you can calculate exactly how much of this stuff is made. You can calculate very accurately how much helium should have been made compared to how much hydrogen you have, for example. You can also calculate deuterium and lithium and other kinds of things. And it turns out that if you go out and you look in areas of the universe that are basically primordial, that stars haven't done much to, or you go out and you look at stars that look like they're very old, that they formed very early on in the universe, then the ratios of these elements that you predict in the Big Bang are very, very almost identically close to what you predict based on this Big Bang calculation, the primordial nucleosynthesis calculation. What that means is we know what the universe was doing 100 seconds after the Big Bang extremely precisely. And if you fiddle around with what was happening at that time, you screw all this stuff up. Are there any questions about that? Yeah.
I have a question going back to the microwave thing.
Yeah.
Can you clarify what you mean by 3 degrees? Because how does that detector detect?
Oh, okay. So this is a question saying, I'm still thinking about, so she says, I'm still thinking about this 3 degree stuff, this background. How can a detector detect temperature, I think is the question. How does a radio telescope detect temperature? So who remembers what a black body is? Someone tell me what a black body radiator is. Yeah. Yeah, it's a perfect emitter of light. And what does temperature have to do with a black body radiator? Good. Temperature is the only thing that gives it light. And specifically, the higher the temperature, what kind of light comes out? Like in terms of its wavelength. Yeah, higher temperature glows bluer, and cooler temperature glows redder. Now with stars, we're talking about temperatures like 5,000 degrees. And we're talking about differences between like 3,000 degrees and maybe 6,000 degrees, going from blue for the hottest ones to red in the coolest ones. And so you can measure if you measure the wavelengths of light coming out of stars, you can measure the temperatures of those stars. You remember that? Okay, do people remember that? So now imagine taking a thing that's like so then imagine thinking about the temperatures of other things, right? So we all glow at black bodies too. We're all black bodies at some level. We emit light, we emit energy, but it's not in visible wavelengths. So if you were to look at the spectrum coming off of us, we have some part of our spectrum that's actually infrared light. That's heat. So we sense infrared light as heat. So you can measure our temperature by just measuring what the wavelength of infrared light coming out of us was. Does that make sense? Okay? That's infrared. I'm talking about now microwave, which is even longer than infrared. So going really long wavelengths. So that, in that sense, that's what I'm talking about is the temperature. I'm talking about measuring the wavelength distribution of light. But instead of that peaking in the visible or in the infrared, visible like stars, infrared like us, this peaks in the microwave. But because it peaks in the microwave where wavelengths are really long, we're talking millimeters, that means it's very, very, very cold. Okay, does that make sense? So that's what I'm talking about when I say temperature. Temperature generally is basically defined by the blackbody spectrum it's emitting. That's what temperature is. Are there any other questions about that? Okay, so let's go back now and talk about nucleosynthesis. So what I'm trying to do now is I'm trying to probe this time after the Big Bang that's even earlier than this microwave background temperature thing. I want to go back even earlier. And so it turns out that you can measure how many light nuclei formed in the Big Bang and compare that to the predictions that we think should have happened. And those numbers are really, really close. And so that's one reason why we think we understand the conditions of the universe at that time quite well. Are there any questions about that? Yeah.
So you said messing with observations that indicate great agreement would screw this all up?
Messing with the story, like messing with, for example, the age of the universe, or messing with how much mass we thought was in the universe, or things like that would screw this up a lot. So everything we know, everything we think we know about the expansion history of the universe, if we change what's happening with, for example, the temperature of the universe at that time, or the rate at which the universe is expanding at that time, all of those things play fundamentally into how many light elements we think are produced. And so in fact, you can these measurements of how much hydrogen and helium and different types of helium and lithium and things like that that were made in the Big Bang allow us to constrain very precisely how fast the universe was expanding, what the temperature of the universe was. It's something like 100 seconds after the Big Bang. Any other questions? So let me just ask this, make sure people are paying attention or understanding me. Why didn't the light elements form earlier than 3 minutes after the Big Bang? Yeah.
It was too hot?
It was too hot. Great. Great. Right. It was too hot. It was so hot before that time that if you would have formed the light elements, everything's moving so fast that they slam into each other and break apart. So you got to wait for the universe to cool down so that things are going slowly enough, and also it's not as dense as it was before, that you don't slam together anymore. Yeah?
I have a question. I remember you said the universe was foggy.
Yeah.
So was that a fog of electrons?
A fog of electrons. A fog of electrons and protons. But it's mainly that you have all these electrons that are free, that aren't bound to their atoms, so they have a charge, and that makes light bounce all around. So like if suddenly there were all kinds of electrons in this room, first of all, we'd all get electrocuted, but you couldn't see me because it would just, the light could not propagate freely. So the fourth pillar, so-called pillar of the Big Bang, is the fact that if you look at galaxies that are really far away and therefore back in the past, they look different than they look today. So that's just sort of direct evidence that things are changing, that if you go look at things back in the past, the universe was not like it is now. And that just gives you this sense that the universe is actually developing over time. So this is a movie, I'm going to show you again, of the deepest image of the universe that's ever been taken by the Hubble Space Telescope. And what Hubble is doing is it's going to point at a spot in the sky that's the size of 1/10 of the full moon. So a teeny tiny little spot on the sky, right here, that looked perfectly dark, like there was nothing there at all. And Hubble points at it and basically opens the shutter on its camera for about 2 weeks and just collects light and lets that signal build up. And the picture that's revealed is just pretty amazing. So this is going to give you, this is a little movie. This just shows you where it is in the sky. And now we're going to zoom in to this single spot. Now we don't have this deep picture everywhere. We only have this deep picture at one single spot because that's where Hubble looked. And there it is. We're coming up on it. It's called the Hubble Ultra Deep Field. And it's the deepest picture of the universe that's ever been taken. And so what you see, these galaxies here, the light from many of these galaxies left them more than 13 billion years ago. And one thing you see right away is that the galaxies at this time look really messed up. They're ratty and knotty, and they have clumps and stuff. And this is one of the really early ones right here. And so the point is that if you look at this image, galaxies here do not look like the Milky Way. The Milky Way is a very smooth-looking, grand design spiral that's got all these beautiful spiral arms and stuff like that. The galaxies you see here, looking way back in time, billions of years ago, something like 500 million years after the Big Bang or so, they look like they haven't quite finished being developed yet, okay? So these are like adolescent galaxies. They're not quite what they're going to be. They're in that kind of awkward tween phase where they're not quite what they're going to be. They're not the beautiful, 20-year-olds that you all are now. And then you have these old, almost dead galaxies like me. They're just over here somewhere. So anyway, so these are the 4 pillars of the Big Bang. Here's a clue. Professors are sometimes lazy on tests. If you have lists of 4, that's a good one to look at. Okay? So make sure you know this one. Now we're going to talk about dark matter. Yeah?
About Big Bang, are there
Yeah.
any other theories besides the Big Bang that...
There's nothing that holds together at all. There were a few theories that were popular in the 60s, and there are a few people kind of hanging on that have these ideas, but there's not many of them. So I would say that there were sort of competing ideas in the past, but today it's kind of the only thing going. The questions that are under debate now is like as you push way back, I'm not talking about 100 seconds, I'm talking about 10 to the minus 35 seconds. I'm talking way back. That's the era now where people are trying to understand what was going on. Was there actually a single point? Were there other processes going on as you approach the beginning? That's where our understanding gets really fuzzy. Basically, as you propagate back to time t equals 0, the temperatures are going up, the energy scales are going way up. And we just can't test conditions like that in the laboratory on Earth. The Large Hadron Collider in Switzerland, who's heard of this? Who's heard of the Large Hadron Collider? Good. So this is a particle accelerator that's taking particles and spinning them around really fast and slamming them together. It's creating energies, effectively temperatures, that are so high that we've never realized them since the Big Bang itself. So in those particle accelerators, we're trying to make temperatures that are very high and effectively in the laboratory probe what was going on in the very fractions of a second after the Big Bang. But as you get you can keep going forever in the Big Bang all the way back, and we just don't have particle accelerators that are big enough to test those energy scales. Okay. So one thing they're actually looking for in the Large Hadron Collider is something called dark matter. A lot of us really hope that there's a signature in the data from this particle accelerator that will betray possibly that there's some kind of new particle in nature that people have been hunting for a long time that can explain a phenomenon in astronomy called dark matter. And that's what I'm going to talk about now. Yeah?
Is that Higgs boson?
No, the Higgs boson is not the dark matter. So,
is it a particle?
Yeah, Higgs boson is a particle. It's not the dark matter, but it's another particle. The Higgs boson is the particle that is responsible for things having mass, turns out. And that looks like it's been discovered after years and years of hunting for it by the Large Hadron Collider. So I showed you this figure last time. This is a pie chart that shows our current understanding of what the universe is made of. Okay? And the weird thing is that only 5% of the universe is made of stuff that like what we're made of. or in fact, anything that we're familiar with is made of. Anything on the periodic table. 70% of the universe is this stuff that's making the universe expand at an ever faster rate. So this acceleration in the expansion rate of the universe, this dark energy that I talked about last time. And 25% is something that's called dark matter. Now it turns out our current best guess for what the dark matter is it's something that's not dark energy. It's very different than dark energy. Okay? But it's not normal stuff either. It's not made of normal atoms. It's made, we think, of some kind of elementary particle of nature that we just haven't detected yet in the laboratory. An analogy to this is something called a neutrino. It turns out that many years ago, we now know that there are particles called neutrinos, and we know how to detect them. But we haven't always known they were there. There was a long time in modern science that we had no idea that there were these particles called neutrinos that we now know are going through us all the time. But eventually they were detected. In fact, the neutrino was detected by Fred Reines, who was a faculty member at UC Irvine, and we have a hall right over there called Reines Hall. So you get a building named after you if you detect these particles. So maybe one of us here will detect the dark matter particle, we'll get a new physics building, which would be great. So anyway, so I'm going to talk about dark matter. We know the universe is expanding. We've been talking about that forever. You're sick of hearing about it. It's all expanding away. This is a map of the local universe. Everything's going out. But not every single point isn't going out. There's some slop in it. Some of it's going out faster than others. Some things are going away faster than others. In fact, here's a diagram that I showed you last time, which plots the Hubble plot. This is the Hubble diagram that plots the recession velocity of galaxies versus the distance to those galaxies. And here's this sort of line-like relationship between them. This is the Hubble relationship that we've talked about before. The slope of this line is the Hubble constant. Now, if you look at this plot, does it look like all the points lie along the line? Who thinks yes? Good. Who thinks no? See, I'm always tempted to ask who thinks, because not everybody has answered. What looks funny here? Does there something look funny in this plot? In the very back, in the middle, with classes. You're in the very back row. Yes, you. Yeah, that thing in the middle. There's something here that looks weird. What's this? What's going on there? These are a bunch of galaxies that are all in about the same place, right? Because they have the same distance. But they're not all moving together in the same direction. Some of them are moving towards us a little, some of them are moving away from us a little slower than others. What this is a cluster of galaxies that are all zooming around each other. Okay? So imagine that they're all going like this. So some of them are going forward and back relative to you, but the whole ball, like a beehive, is actually going away with the expansion of the universe. So that actually gives you a much better picture of what the universe is really doing. There's kind of pockets of stuff that are sort of orbiting around each other, but globally that pocket is going away from us with a large-scale universe. In particular, our story with dark matter begins with one of these balls of galaxies called the Coma cluster. The Coma cluster is kind of the biggest, baddest cluster of galaxies that's near us. It's got thousands of galaxies in it, and it's a place where it's useful to study what's going on. It turns out that you can measure the mass of one of these clusters by measuring how fast the galaxies are moving. Okay? And the basic idea is the slower the galaxies are moving around each other, the less mass this whole thing has. And the faster they're moving around each other, the more mass it has. Okay? And the way to think about it is, there's a certain velocity that you can have, and if it's higher than that, you'll escape. There's not enough gravity for you to be there. Okay? So if you had, you know, a satellite going around the Earth at 1,000 times the escape velocity of the Earth, it would just fly off. It would not orbit around the Earth. So the idea is if you see galaxies moving around really fast, either they're destined to just fly away from each other really soon, or there's a lot of mass there to hold them there. And so the basic idea is that if you measure small velocities for galaxies and galaxy clusters, there's not much mass there. But if you measure high velocities, then that means there's a lot of mass. Does that make sense? So here's this coma cluster, modern picture of it. And in 1933, this guy named Fritz Zwicky was looking at these galaxies. And he measured how fast they were moving. And what he found is that they were moving really fast. Way, way faster than he thought they should be moving, based on how much mass he could count in the light from the galaxies. So he could count how many galaxies there were. He knows how much a galaxy weighs roughly, adds up all that mass. It's not nearly enough to explain all this stuff. And he says, look, there's got to be something else there, and I can't see it. So there's some kind of dark matter there that's holding this stuff together. So this is the first time that people started talking about this idea of dark matter. Now, Zwicky didn't know what it was, but he just said, look, there's got to be a lot more mass there than I can see. It doesn't shine, so I call it dark. Now, Fritz was a very interesting character, this guy. You can kind of tell from the picture. That's why I like this picture. That's pretty much it. That's his deal right there. So not everybody took him seriously. Okay? They didn't know what was going on with it. And in fact, there was another guy who looked at another cluster nearby called Virgo and saw the same kind of thing. But people didn't really know what to make of it. Now today, if we go back and we look at these kind of clusters, I think this is coma again. Now we have X-ray telescopes. They didn't have them back then. Now if you point an X-ray telescope at this cluster, it's booming an X-ray light too. And what that says is there's a hot gas there, and you can measure it's got tremendous pressure. That's hot gas in the coma cluster has got all kinds of pressure. And again, because it has so much pressure, you need gravity to confine it, or else it would float away. And the mass you estimate from the pressure of the hot gas that you can measure from X-ray is very similar to the mass you estimate from how fast those galaxies are going around. But again, Fritz didn't have this, and so people didn't believe him at the time. Well, maybe they believed him, they just didn't know what to make of it. Let's flash forward to around 1965. It was at this time that astronomers now had really had developed ways of measuring velocities very precisely over the face of a galaxy. In particular, one of the pioneers of this is Vera Rubin. Vera is alive today, and actually her son is a chair in the mathematics department here at UC Irvine. What she was expecting to see is she was expecting to see the stars in the middle of these galaxies spinning really fast, but then as you go out to the edge, she thought that the velocities would drop off. And this is just the same way, and that's because there's more mass in the middle, there's more light in the middle than in the outer part. This is just the same way that Mercury and Venus are going around the sun much quicker than Pluto. That's because the gravity from the sun is much smaller way out there compared to where in close. Okay? But this is not what she saw. When she actually went out and measured it, what she found was that the rotation curve was very flat. So you expected it to fall off, but instead these stars way out here were whipping around much faster than you thought they should be. And again, now we interpret this as dark matter. You see this basically every galaxy you look at. Every single galaxy you look at basically shows this. If you look out far enough, there's anomalous velocities. Things are moving much faster than you think they should move. And so now we have this idea that around all galaxies is this big distribution of missing mass, this dark matter. Now, there's a lot more evidence for dark matter now. So, you know, scientists are generally very skeptical people. And when this kind of stuff was originally coming out, forget about crazy Fritz. I mean, even here, when this stuff was coming out, scientists were like, okay, this is nuts. This can't be true. But since this time in the 60s and today, there's just more and more evidence that builds up from a process. Something called gravitational lensing is one way. There's other things you can do, looking at things in the distant universe. There's lots of different ways that things are kind of coming together that are all pointing to this picture that there's this mysterious missing mass out there that we can't explain. Let me give you one other example that gives you a sense of the complexity of this whole problem, but how everything fits together very nicely. If you recall back when I was talking about the Big Bang before, there was this detection of what I said was the cosmic microwave background. The fact that everywhere you point in the sky with a radio telescope, you see that the universe has the same temperature everywhere, 2.7 degrees Kelvin. So this is supposed to be a map of the sky. That's what this is. And it's all the same color because it's all the same temperature. Now, it all being exactly the same temperature is a little bit weird. Because if you start off with a universe that's perfectly smooth, how does anything ever grow? How do you start off with a universe that's 100% perfectly smooth and then have structure emerge from it? We look out in the universe today, there's structure everywhere. There's galaxies all over the place. So how do you go from something that has absolutely zero, nothing, to structure all over the place? Now the way you do this is with gravity. If you just have anything, give me anything, any little bitty blip where it's a little bit more dense than other places, gravity will say, oh, I'm going there. Because if I have a little bit more mass than everywhere else, gravity will then make that place even more dense pretty soon. And so what cosmologists were doing ever since this original detection in 1964 is they were trying to see some differences, some ripples in this temperature distribution. And they hunted for it. They went back and they looked again, still nothing. It was smooth to 1 1/10. Then they went back and looked again with even more powerful instruments. It was smooth to 1 part in 100. Man, this is getting kind of scary because, I mean, at some point there's just not enough mass in the universe to start out with a universe that's that smooth and grow to all the complexity we see today. So then they look again and they find that it's smooth to 1 part in 1,000. So now people are starting to get nervous, like, wait a second, maybe we don't understand what's going on. Maybe we're misinterpreting this whole signal. Maybe this is something else. Finally, in 1990, with a satellite called COBE, it was detected. Differences. Differences to 1 part in 100,000. So you needed 1 part in 100,000 discrimination to see minor temperature differences. So what this is a temperature map. These spots are hotter and these spots are colder, but they're only hotter by 1 part in 100,000. And since this detection, then in 2003, there was a new satellite called WMAP that really refined it. And so this, in some sense, is a baby picture of the universe. This is that the universe actually did have some structure at early times, but it was very smooth. But it was so smooth that there's this puzzle. How do you go from a universe that's smooth to 1 part in 100,000 to all the rich complexity of galaxies and everything that we see today? Well, one way you do it is you add additional matter. If all you have is normal matter, the stuff we see, hydrogen and helium, the stuff that we know was made in the Big Bang, if we only have that, you cannot make the large-scale structure of the universe as we see it today. But if you take a large simulation, make it almost perfectly smooth in the beginning, and put all this dark matter in, according to the composition of the cosmos that we think is there, and you run it forward over time, what you find is that those little bitty initial clumps grow and grow and grow. They're amplified by gravity. And what you're seeing here is these dark yellow points are places where there's more stuff. They're denser. And the lighter green is lower density. So what's happening is the galaxies are forming in these yellow clumps. And they're also forming along these kind of networked filaments. You can kind of see it here, that they're sort of like these big open bubbles in the middle. And those things are sort of flanked by these filamentary structures. This is 200 million light years across, and it's a universe simulated in a supercomputer. And the idea here is that each of these yellow clumps harbors within it a galaxy. Now the amazing thing is, if you run these kind of simulations, putting the dark matter, and actually you have to put the dark energy in and all this kind of stuff, they look like these red maps here. So these are like wedge diagrams. If you just try to observe the simulated universe in the same way we observe the real universe, you get distributions of galaxies that look like this. And this is, you would interpret this as locally around the Earth, and then this is clumping of galaxies all the way out for billions of light years. These blue wedges are actually real observed galaxies in the universe. So what you can see is it's not, perfect, but in a statistical sense, that's all you can predict. In a statistical sense, these two sets of this theory versus the observation are identical. You can't, they're indistinguishable statistically. And you can kind of look at it by eye and you're like, hey, it's pretty close. Okay, if I hadn't told you which was which, you would say, I don't know, they look kind of the same. And so it's pieces of evidence like this that we have these kind of indirect pieces of evidence that there's this weird dark energy stuff going on, there's this weird dark matter stuff going on. But it turns out that you can't explain even things like the large-scale structure of the universe unless you put that stuff in. But when you put it in, you get it all right. Now, we don't know what that stuff is, but we know we have to put it in to get the universe right. Yeah?
Is that Einstein, the constant that Einstein had? Or is it
This is with the constant that Einstein had. So this simulation is with the cosmological constant and not a weirder kind of dark energy. So it turns out the standard old boring cosmological constant of Einstein is the model that works really well for this kind of stuff. Anything else? Okay. So, like I was telling you, lists. Everybody, I like lists. So what's the evidence that we have for dark matter? So first, there's the fact that galaxies are moving fast in galaxy clusters. You couldn't explain the speeds of those galaxies if the only mass you had in the galaxy clusters were just the galaxies themselves. The second is that there's hot gas in galaxy clusters that has so much temperature and pressure that you could not confine it there if there wasn't additional mass there to hold it. The third is if you just look at how fast galaxies are spinning. Okay? You would expect that galaxy spins, the rotation speeds of stars at the edges of galaxies begin to get smaller and smaller as you go out, but that's not what you see. What you see instead is it's rather flat. And that's indicative of there being a lot of extra mass out there that's allowing those stars to go fast and not fly off. And finally, I talked about the large-scale structure of the universe itself. The universe is very, very smooth at early times. We know that. We can see it directly in the cosmic microwave background. But the universe, when we look around us today, is just crisscrossed with galaxies everywhere we look. And the only way to go from that smooth beginning to that really complex and clumpy universe we see today is to have a lot of additional mass there. Now, it turns out there's actually a lot of other pieces of evidence that the dark matter is there, but I haven't had time to talk about it. So as we talk about this pie chart, this, what the universe is made of, one way to think about the differences between these things. So people are constantly asking me, like, is dark energy and dark matter the same thing? The answer is no. They're sort of almost at opposite. They're trying to do opposite things. The dark matter is actually the engine of galaxy formation. The way we understand it now, if the dark matter wasn't there, it would be almost impossible to make galaxies. Which means it wouldn't be possible to make stars that then recycle new elements that they made. So there would be no complex chemistry. Okay? So if there wasn't for dark matter, it's not obvious that there would be us. It's unclear how we could possibly form life in the universe without this additional stuff. Whereas dark energy kind of does the opposite. Dark energy is trying to drag stuff away from each other. It's trying to fight that tendency for things to collapse gravitationally. It's trying to make the universe expand at accelerated pace. So at some level, the dark energy is sort of trying to do the opposite thing. And it just so happens over the course of history of the universe so far, the dark matter has won. We actually think that in the long run, the dark energy is going to win. Okay. Are there any questions about that? Okay. All right. So this is the end of this class, and so what I want to do now is provide kind of a perspective, a summary of what we've been doing here in a slightly different way. So about 100,000 years ago, somehow, the complexity that the universe creates ended up developing the human pupil, which was stuck onto our brain. That pupil is about 0.3 inches in diameter. And so with that tool that we were born with, you can look up at the sky and you can learn things. You can learn that the patterns of the stars are regular, and that where certain constellations are in the sky can tell you things about, like, for example, when it's going to be summertime, when it would be a good idea to plant food or go hunt for certain things. By looking at the sky with those eyes, eventually you can come up with ideas like, hey, the Earth is actually round, even though it might seem to be flat. And maybe it allows you to come up with the idea that even though it seems like the sun is going around the Earth, that doesn't actually jive with quite everything I see. Maybe it's the other way around. In 1620, Galileo built himself a bigger lens. It was 2.5 inches in diameter. And with that extension, again connected to his brain, he was able to show, yeah, for sure, we're definitely going around the sun. And that little light up in the sky that we call Jupiter has other things going around it. Venus has structure and the moon has mountains. And it's very likely that those other stars up in the sky are other suns. And so suddenly we realized that the universe is much bigger than we had ever imagined it to be. Galileo never imagined that Jupiter had moons before this telescope. Nobody did. I'm going to do a new scale now. That's Galileo's 1.5-inch telescope, that little dot. In 1917, the largest telescope in the world was 100 inches, 60-something times bigger than Galileo's telescope in diameter, but much more powerful. Before this telescope was built, no one had any idea that the universe was accelerating. It was expanding. In fact, before this telescope was built, we didn't know what the nature of the universe was at all. We didn't know that there were other galaxies. We thought that the whole universe was basically stars. But with this powerful telescope, Hubble was able to show that Andromeda was actually a galaxy in its own right. It was more than 1 million light years away, and that the universe itself was expanding. The biggest telescope in the world right now is the 10-meter Keck telescope. The most powerful optical telescope in the world are the 10-meter Keck telescopes in Hawaii, built in 1993. Before these telescopes were built, we had no idea that dark energy was there. We didn't know the universe was expanding. In fact, when I was in graduate school, there were a lot of theoretical cosmologists who told me that that was insane, that you should never imagine a universe that was accelerating. That doesn't make any sense. But only because of observations with the Keck telescope were we able to measure this precisely. And again, overturn the ideas that we had that we didn't even think about before it was built. Currently, the University of California is in partnership with Canada, Japan, Caltech, China to build something called the 30-meter telescope. Now, I'd like to tell you about all the things that we're going to discover with this telescope, because there are things that we'd like to look at. But it's highly likely that whatever we do discover is things that we haven't thought of yet. Maybe the universe is even weirder than our imaginations can conceive right now. So stay tuned for that. And that's it. So I've put this study guide up online. Hopefully that'll help you. And I'm happy to take questions over email or in office hours tomorrow. So thanks very much.